Welcome to AI Paper Slop. Today we are looking at Echo Infinity, learning evolving memory for real-time infinite video generation.
Yeah.
And look, we are skipping the preamble today because if you're training or running autoregressive video diffusion transformers, DITs, you know exactly what happens when you try to generate a long sequence.
Oh, yeah. You inevitably crash into two massive brick walls.
Right. First, you get this unbounded key value or KV cache growth, and that triggers a massive out-of-memory error. And then second, you hit temporal rope E index overflow.
Which just completely shatters the generation quality, right? It turns your video into this colorful, overexposed mess.
Exactly. But Echo Infinity completely solves both bottlenecks, like fully solves them. They introduce these end-to-end learnable memory queries that dynamically compress history at a strict, constant compute cost. Plus, they deploy this unified relative rope E recipe that entirely eliminates the train test mismatch.
And the result is just wild. Real-time, 24-hour video generation.
Yeah. Over 1.3 million frames running on a single H100 GPU at 18.5 frames per second with zero degradation. Yeah. It's crazy.
It's a phenomenal engineering achievement, honestly. I mean, the field has been struggling with this specific dual bottleneck for a while now.
So let's break that down for people. Why is hitting that 24-hour mark on one GPU such a huge leap?
Well, you have to look closely at the math behind how autoregressive models handle temporal consistency. When an AR model generates video frame by frame, the attention mechanism relies heavily on the KV cache to remember the past.
Right, it's storing the keys and values for every single token.
Exactly. And because you are generating continuously, that cache scales linearly with time. For every single new frame you push out, the cache inflates.
So it just gets bigger and bigger.
Yeah, it is a strict mathematical guarantee that you will eventually run out of VRAM. The system just panics and triggers an ohm error.
And if you've ever waited hours for a model to render a scene, only for the GPU to just die at the 2-minute mark, you know how painful this is.
Oh, it's the worst.
You literally cannot reach infinity if your memory footprint grows with every step. But, I mean, it's not just the memory limits we have to worry about, right? There's also the positional bottleneck.
Correct. So modern video DITs rely on 3D rotary positional embeddings, or ROPE, to inject spatial and temporal awareness into the tokens.
Right.
ROPE basically works by rotating the feature vectors based on their position. But during training, the model is only exposed to temporal IDs up to a hard maximum.
And for this paper, they're building on the WAN 2.1 base model, right?
Yes, exactly. And that model has a maximum temporal ID, they call it FEFmax, of 20. So the attention mechanism learns to perfectly balance the rotation angles for frames 0 through 20.
Okay, but when you deploy this for continuous streaming, eventually you have to ask the model to generate frame 21.
Yeah, and the model receives a rotation angle it has literally never encountered in its training distribution.
So what happens? Does it just guess?
It tries to extrapolate beyond its trained bounds, and the attention matrix just breaks down. The logits explode. Within a handful of frames, you get severe color shifts, artifacts, and just total structural collapse.
Wow. Okay, I was thinking about this earlier. And imagine watching a highly skilled improvisational actor trying to perform a play.
Okay, I like where this is going.
So the actor is our DIT. They're brilliant, but they have a literal hoarding problem. And they are performing on an incredibly tiny stage.
Right, so the hoarding is the KV cache.
Exactly. As the play goes on, they pick up every single prop, teacups, swords, chairs, and they just refuse to throw anything away. Eventually, they're buried under a mountain of junk and can't physically move. That's our OM error.
That's perfect. And the tiny stage is the rope E limit.
Right. The actor has only ever practiced walking exactly 20 steps in one direction. The moment the script forces them to take step 21, they just walk right off the edge of the stage into the orchestra pit.
That is a great visual. But the hoarding analogy, it's actually much worse than just carrying the props.
Wait, really? How so?
Well, the actor isn't just holding them. Before delivering every single new line of dialogue, they are actively scanning every single prop they've collected since the curtain opened, just to make sure their next line makes sense.
Oh, wow. So the computational cost of just referencing that history becomes suffocating?
Exactly. And this is exactly why researchers have been trying to hack their way out of this problem for the last year.
And those prior hacks are fundamentally flawed, which the paper points out politely but firmly. I mean, the most basic fix for the KV cache problem is window truncation, right?
Yeah, which is basically just dumping the props off the stage.
Right. You keep a few initial sync frames to ground the scene. You keep a local window of the most recent frames. and everything else just gets deleted.
And sure, it solves the memory limit, but it gives your AI the memory of a goldfish.
Right.
If your character walks out of a room wearing a spacesuit and the camera pans away for 30 seconds, the model has deleted the spacesuit from its KV cache.
So when the character walks back in, they might be wearing a tuxedo.
Exactly. The model acts like nothing happened. The entire semantic thread of the video is just lost.
Which I guess led to slightly smarter approaches like handcrafted management. Because I know methods like MemFlow try to solve this by using rule-based retrieval.
Right. They essentially set up a rigid set of rules to sift through the evicted KV tokens and decide, what to keep in memory bank.
But why does that fail? It sounds decent in theory.
The issue is that handcrafted rules are entirely decoupled from the actual generation process. They're tuned offline. But when you are generating video autoaggressively, errors naturally compound.
Ah, okay. So a small amount of noise in frame 500 might require specific contextual data from frame 400 to correct.
Exactly. And a rigid retrieval rule won't know that. It doesn't adapt to the specific noise dynamics of that specific run, so it eventually retrieves the wrong context, and the whole generation drifts.
Okay, so truncation is too destructive, and handcrafted rules are too rigid. What about compressing the history, like heuristic compression methods?
You mean like memorize and generate?
Yeah, where they try to shrink the past down using a fixed ratio. So you compress the historical frames by 10x. Doesn't that solve it?
Nope, the math still defeats you. If generation time, let's call it t, goes to infinity, your memory footprint is still O of t divided by c, where c is your compression ratio.
Oh, I see.
Yeah. So if you compress 1 hour of video by 10x, you still have 6 minutes of incredibly dense token data just sitting in VRAM. 10 hours of video leaves you with an hour of dense data.
So the footprint is still unbounded. It just delays the inevitable ohm crash.
Exactly. It just buys you a little more time.
Okay, so if compressing data at a fixed ratio mathematically guarantees we still run out of memory eventually, we have to stop treating memory like a hard drive.
Yes.
We have to treat it more like a brain. And that is the massive paradigm shift in Echo Infinity. They look directly at cognitive neuroscience for the architecture.
It really is a brilliant mapping of working memory versus long-term consolidation.
Yeah.
Because when we experience the world, we don't store raw pixel data of every second of our lives.
Right. I don't remember every single leaf I saw on my walk this morning.
Exactly. Fresh perceptions enter our short-term working buffer. But when that information leaves the buffer, it isn't completely deleted, and it isn't zipped up like a computer file either.
It's selectively filtered.
Yes. The semantic essence is abstracted and consolidated into a highly compact long-term state that just updates dynamically.
But wait, let me push back on that for a second. If human memory is the inspiration, aren't we still dealing with a fixed capacity limit? Like the brain definitely has limits.
Sure.
So if these new memory queries in the model have a strictly fixed size, how do they not just overwrite the most important stuff over time? What makes this different from the goldfish memory of window truncation?
That is the million-dollar question. The key difference is end-to-end optimization. The memory isn't just blindly overwriting the oldest data based on some timeline.
Okay.
To see why this works, we really need to look at how they structured the 3-tier KV organization for every single transformer layer. Because they cap the total memory footprint at just 15 frames of data.
Wow. So no matter if you generate for 1 minute or 24 hours, the model never references more than 15 frames worth of tokens.
Exactly 15. So first, you have the sync frames, which is 3 frames. These are persistent global anchors. Early research showed that the first few frames of a sequence absorb massive attention scores, right?
Yeah, they kind of act as a stabilizing force for the attention matrix.
Exactly. So those 3 frames never leave. Second, you have the local window, which is 9 frames. This is your high-fidelity short-term working buffer containing the immediate past.
Okay, so 3 plus 9 is 12. That leaves 3 frames.
And that is the third tier, the memory queries, or 3 frames. But here's the catch. These aren't raw image frames. These are trainable, evolving tokens that summarize the entirety of the evicted history.
Okay, but how does all that evicted history actually get packed into just 3 frames worth of queries? Like, when frame number 10 slides out of that 9-frame local window, it doesn't just vanish. What physically happens in the architecture?
This is what they call the eviction update mechanism. The evicted KV cache from the local window is routed into a cross-attention encoder.
Okay.
And in this encoder, the current state of the memory queries, let's call that matrix Q acts as the query, while the evicted frames act as the keys and values.
So Q is actively probing the departing frames.
Exactly. It's asking, what semantic information in here is critical for generating future frames.
That's extracting the features it needs.
Yeah.
But it can't just forcefully jam that new data into the Q tokens,
Sure.
right? Or the state would become totally chaotic.
Right, which brings us to the mathematical core of the update, the sigmoid-gated residual mechanism.
Okay, break that down for us.
So once the cross-attention extracts the new information, let's call it new Q, the model computes a gate value using a sigmoid function. This gate evaluates both the old memory Q and the new Q.
And it balances them.
Right. It basically says, okay, Q gets updated by taking a percentage of the old Q plus the remaining percentage of the new Q.
Let me put that in a real-world scenario because I love analogies.
Go for it.
Think of the sigmoid gate like a bouncer at a very exclusive maximum capacity nightclub. The club represents our memory queries.
Okay, I see it.
When a new group of people, so the evicted frame, shows up, the bouncer doesn't just kick out an old patron to make room. Instead, the bouncer evaluates the vibe of the new group against the existing vibe of the club.
Yeah.
They intelligently merge the core essence of the new arrivals with the long-term atmosphere of the room. The gate decides what percentage of the old memory to keep and what percentage of the new memory to let in, ensuring the overall state remains perfectly balanced.
That captures the balancing act perfectly. And because this bouncer, the gating function, is trained end-to-end alongside the diffusion model, it learns exactly what features are causally necessary to maintain video consistency.
It actually learns what's important.
Yeah, and the paper highlights an ablation study that proves how vital this is. When the researchers disabled the sigmoid gate and forced a simple residual update, basically letting the new memory directly overwrite the old, the entire system destabilized.
Really? Like what happened?
Backgrounds flickered, subjects warped, and the memory state just lost its coherence. The gate absolutely protects the historical integrity.
Wow. Okay, so that brilliantly solves the hoarding actor problem.
Yeah.
The KV cache is strictly bounded to 15 frames no matter how long the video runs. We have a constant compute cost avoiding the OM crash.
Yep.
But our improvisational actor is still standing on a tiny stage. We still have to fix the ropey index overflow. Because if our local window keeps moving forward in time, eventually the token IDs are going to hit 21 and the model collapses.
Right. And this brings us to why concurrent attempts to fix positional overflow have failed.
Like infinity rope.
Exactly. Methods like infinity rope attempt to fix the clock entirely at inference time. They let the model generate normally up to the Fmax limit of 20. Then they intercept the generation and say, okay, reset the clock, shift all the temporal indices so the newest frame stays within bounds.
Which honestly sounds completely logical. If the limit is 20, just keep resetting it to 20. Why does that break the video?
Because it creates an aggressive train-test mismatch. When the base model was trained, it learned that position 0 means the absolute beginning of the visual physics, and position 15 is absolutely position 15.
Oh, I see.
The attention weights are highly optimized for those absolute relative distances. If you suddenly shift to a sliding relative window during inference, the attention mechanism receives signals that violate its training distribution.
So the model gets confused about the flow of time.
Exactly, resulting in those severe color shifts and overexposures we mentioned earlier.
Right. You can't train a model on an absolute timeline and then test it on a relative timeline. So Echo Infinity has to implement the fix during the training phase itself.
Yes, and they created what they call the Unified Relative Rope recipe. And the word unified is the key here. It is applied symmetrically during both training and inference.
Okay, so how does it mechanically work?
So the sync frames are permanently anchored at temporal ID 0. When generation begins, the system enters the growth phase. The newest frame ID increments normally 1, 2, 3, all the way up to Fmax, which is 20.
So far, behaving exactly like the base model.
But the moment the newest frame hits 20, the system shifts into the mature phase. The temporal ID for the newest frame locks at 20. It will never become 21.
Wait, then what happens to the older frames?
To maintain the correct relative distances, all the older active frames, everything in the local window and the memory queries, are mathematically rotated backward.
Oh.
Yeah. The frame that was at position 19 is reassigned to 18, position 18 becomes 17, and so on. The newest frame just remains at 20.
It's a treadmill.
Yes.
Instead of the temporal IDR runner sprinting off the front of the machine into the ropey overflow wall, the treadmill belt suddenly engages once the runner hits the front. As the runner keeps stepping forward to generate new frames, the belt pulls the old temporal landscape backward beneath them.
Exactly.
Every single frame generated stays perfectly within the 0 to 20 index bounds.
The treadmill is the exact physical intuition. And because the researchers distilled the base model into this specific relative sliding window behavior during training, the model's attention weights are completely comfortable with the older context continuously shifting backward.
So there's zero mismatch between what it learned and what it's being asked to do at runtime.
Zero mismatch.
Okay, we have bounded, evolving memory queries, acting like human consolidation, combined with the temporal treadmill that prevents the rho p index from ever overflowing. The theory is airtight. But the real test is when the rubble meets the road. What do the actual benchmarks look like?
The headline result is staggering. They set up a single NVIDIA H100 GPU and just let the model run. It maintained 18.5 frames per second and generated a continuous, coherent video for over 24 hours.
24 hours. That is 1.3 million frames.
Yeah.
If you're an ML engineer listening to this, just think about the compute savings there. Generating a million-frame video without a massive multi-node cluster. Just a single GPU efficiently updating its 15-frame memory state. It's wild.
And it isn't just about speed either. The visual stability absolutely crushes the baselines. The paper provides these side-by-side visual comparisons using a prompt of an astronaut walking through ruins.
Oh, I saw those.
Yeah, with models using truncation or handcrafted rules like long-live or memflow, you see severe identity drift over long horizons.
Yeah. The astronaut suit gradually changes design. Or worse, the helmet visor slowly melts into a human face.
Yeah, it's pretty disturbing. The model just forgets the core identity of the prompt.
And what about the heuristic compression models, the ones using fixed ratios?
They fare even worse at the 24-hour mark. Because of the compounding errors inherent in fixed ratio compression, the signal gets completely shredded. The astronaut video literally degrades into static and noise.
Wow.
Echo Infinity, by contrast, maintains the structural integrity of the suit, the textures of the ruined environment, and the temporal flow for hours on end.
You know, there's a secondary finding in this paper that I actually think is a massive hidden gem. They tested what they call the short video prior.
Yes. This was a fascinating ablation. They tested Echo Infinity on standard 5-second videos. Very short generations where you wouldn't expect memory bottlenecks to be an issue anyway, right?
Right.
But here's the twist. They completely disabled the memory update mechanism.
Wait, really?
Yeah. The cross-attention encoder and the sigmoid gate were just turned off. They only provided the model with the optimized initial state of the Q tokens that resulted from the training process.
And it still beat the base models at rendering short clips.
It outperformed comparable models across the board in visual quality, motion smoothness, prompt adherence, even without actively updating the memory.
Think about the implications of that for a second. How does an empty memory state improve short video generation?
Well, the researchers used a technique called distribution matching distillation, or DMD, during training.
Right, and DMD basically forces a student model to match the complex distribution of a highly capable teacher model.
Exactly. By forcing the Echo Infinity student model to aggressively compress and hold on to the vital physics of the teacher's long context videos, they baked a video generation prior directly into the static weights of those Q tokens.
It acts as an incredibly powerful regularizer. Like the paper shows an example of generating a shovel hitting soil.
Oh, that's a great example. Standard models struggle heavily with the complex physical interactions like that. The dirt looks floaty, or the shovel just clips right through the ground without any impact.
But Echo Infinity generates the physical impact, and the plausible dirt splashes perfectly.
Right.
Because if a model is forced to compress the concept of digging into just 3 memory frames, it can't just memorize the pixels. It has to deeply understand the underlying causal physics of the shovel in the dirt.
It learned physics better simply by being forced to learn how to remember.
Exactly. Optimizing for extreme long-term memory compression inherently optimizes for physical understanding. You cannot compress what you do not fundamentally understand.
That's spot on.
So bringing this all together, Echo Infinity has completely shattered the ceiling for autoregressive video generation.
It really has.
By discarding the idea that memory is just this passive storage locker that you fill up until it breaks, and instead treating it as an evolving, learnable state, alongside putting the temporal indices on a unified treadmill, they've eliminated the 2 massive roadblocks to infinite rollout.
They've proven that generating infinite video doesn't require infinite compute or infinite memory. It requires an architecture that actually knows how to consolidate the past.
And that leaves us with a truly massive concept to think about. We framed all of this around generating a video of an astronaut or a shovel. But if we now have a transformer architecture that can perfectly compress, abstract, and retain a constant memory state over 24 hours of highly dynamic visual input, what happens when we apply this evolving memory structure outside of video generation?
Oh man, the possibilities.
Right. Think about physical robotics. Think about continuous learning AI agents navigating complex environments. If a model can remember visually forever without its context window overflowing or its VRAM crashing, we aren't just looking at a better video generator. We might be looking at the foundational architecture for an AI that can genuinely experience and adapt to a persistent world over a lifetime. It was a profound step forward.